Hello, this is chapter 7.1. We are going to be looking at internal forces. If you notice, I have a simple beam drawn on the screen, beam AC, and at this point right in the middle, at point B is what we're going to call it, I'm going to look at the forces internally on the beam due to the forces P1 and P2. Now, we can show internal shear and bending in a beam using the method of sections. We can do it graphically. We can analyze forces in the shape of cables supporting various types of loadings. And why would we do this? Well, we want to make sure that whatever load that's being put on a beam, that the beam material is going to be able to withstand it and not fail due to the loading. So let's go ahead and draw what I'm going to call the free body diagram of this. And I'm going to cut this at A. So I'm going to draw the free body diagram of the left side and the free body diagram of the right side. So let's try that again. So I'm going to have my reaction forces. So I have AY and I have AX. I have this loading here. Now it would have a distance from some point, but since I'm not showing a distance, it's okay for now. This is point B, so I'm just going to label that point B right there. And then I'm going to draw the free body diagram of the right side. That's as good as it's going to get today. And I have my reaction force, CY, and I have loading P2 here, and I still have my point B here as well. So when I look at this and I cut this beam, I have three types of forces that are acting at point B. Actually, anywhere on the beam, I just have isolated point B just for example. I'm going to have what's called shear. And that's shear at point B. I'm going to have a shear force, B, and then I have my normal force, and that's going to be coming off of both sides. And I have my shear force here as well. And then I have a bending moment. Moment about B, and this side over here, moment about B on that side there. Now, how I have drawn these and how I am showing these is positive. Okay, so my moment about B is bending, and if it's being held here, what's happening to this beam is it's starting to do this, right? It's bending, and it looks like a smile, so that's a positive bending moment. The shear will always, a positive shear will always rotate it clockwise. Okay, so if you notice, this shear is rotating this beam clockwise if I'm holding it here. If I'm holding it at point A, rotating it with this shear, it is rotating it clockwise. And again, this moment here is also making this beam kind of do this, which is making it positive. So if it's making it smile, it's a positive. So I think part of the best way to show these is with examples. And so I'm going to go ahead and jump into an example right away. Let's look at this example here. So I've got a beam, simple beam. Let's go ahead and label our points here. I've got point A, and I've got point B. B is my pin and A is my roller. I've got a 10 kilonewton force acting 1.5 meters away from B, and a 30 kilonewton meter moment acting at the end of the beam, or the front of the beam, beginning of the beam, whatever you want to call it. And I'm going to internalize and look at the forces acting at C. Forces acting at C. So the procedure is to solve for the reaction forces. cut the beam and draw a free body diagram, and then use equilibrium equations to solve for our internal forces. Okay, so if I sum my moment about point A, I can get B. So if I redrew this really quick, I'm going to have BY, I'm going to have AY, oops, AX. I've got my moment that's acting on the beam, and then I have 10 kilonewtons. Again, this is 1.5 meters. We're looking at point C. That's 1.5, that's 1.5, and that's 1.5. Okay, so if I sum my moment about point A, I'm calling counterclockwise as positive. I can say that 30 kilonewton meters is positive plus BY times 3 meters minus 10 kilonewtons times 4.5 meters is all equal to 0. I get that BY is 5 kilonewtons. 5 kilonewtons here. And if I sum my forces in the Y, I'm just going to have 10 kilonewtons going down, my 5 kilonewtons going up, which was BY, plus AY is equal to 0. AY comes out to be 5 kilonewtons as well. So those are my reactions. Okay, so now I'm going to look at the left-hand side. So I'm going to look from the end of the beam to C, and I'm going to draw that free body diagram. So here's my beam. I have my reaction force, which was 5 kilonewtons. I have my 30 kilonewton meter acting on the beam here. This was a distance of 1.5 meters, and this is also a distance of 1.5 meters. And then I'm going to draw my reaction, or my internal forces here. So I have my normal, I have my shear. Now I'm drawing that so that it's rotating this beam clockwise, and I have my moment about point B here. Now I just use my equilibrium equations to solve for these. I'm going to say that this is point C, this was point A, and I'm going to sum my moment about point C. So when I sum my moment about point C, I get rid of the shear. The shear I don't have to worry about because there is no perpendicular distance. So I have moment about B, which would be moment, this is moment about C, not B. Moment about C, and I am showing it going counterclockwise, which would be positive. This is also 30 kilonewton meter, which is also positive, so I'll draw that in there, or write that in there. And then I'm subtracting this 5 because it is making it rotate clockwise, so it's a negative 5 kilonewtons times 1.5 meters. It's all equal to 0. So the moment about C is going to be negative 22.5 kilonewton meters. So it actually has a negative bending moment. It's actually making it frown. So I have solved for my moment, bending moment about point C. And then if I sum my forces in the Y is equal to 0, I get that I got 5 kilonewtons minus my shear is all equal to 0. So my shear is equal to 5 kilonewtons, and that is positive. So I got my two answers there. I'm going to put up one more example. This is pretty straightforward. If you have questions, please post them on the discussion page. Thanks.